Okay, Assalamualaikum. We're going to continue on with the last part of chapter 7, okay, which is on the iron and iron carbide phase diagram, right? So, this is how the iron and iron carbide phase diagram looks like, okay? And at this end, okay, we have the point for pure iron, okay, which is 100% iron here, okay. So pure iron actually has like 3 electrodes, okay. It means, okay, it can exist, okay, in different form depending on the temperature that it exists, right? So at room temperature, okay, the stable form is called the alpha ferrite, okay, and it has a BCC crystal structure, okay. So this is the alpha ferrite, right? So alpha ferrite actually exists over a very narrow range, okay, here, right? And as we go vertically along the line, right, so it means the temperature increase, okay, when it reached 912 degrees centigrade, okay, the alpha ferrite will experience a transformation into austenite, right? So austenite has an FCC crystal structure, okay, so this is austenite, right, and austenite has FCC structure, okay. So the area of austenite, okay, is quite vast here, okay, and it stretch over quite a range of temperature, all right. So as the temperature increase, okay, up to 1394 degrees centigrade, okay, the transformation will takes place again, whereby austenite will change into delta ferrite, okay. So this is a small area here, okay, is the area for delta ferrite, all right. And a delta ferrite has a BCC crystal structure, all right. So that's for the left hand side, all right, of the phase diagram, okay. And then let's have a look at the right hand side of the phase diagram, okay. So even though this is actually an iron carbon system phase diagram, okay, but it is commonly known as the iron and iron carbide phase diagram, right? The reason being is that, okay, normally for a phase diagram, okay, you'll see like it's for binary phase diagram, okay, it's between two component or two element, okay. So on one side, okay, we'll have like 100% of element A, and on the other side normally we'll see 100% of element B, all right. But then, okay, it's the same, it's a bit different for iron and iron carbide phase diagram, all right, because just now we have looked on the left hand side of the phase diagram, okay. So we can see that there is 100% of iron, okay, which is for pure iron. But then when we go into the left hand side end of the right hand side end of the phase diagram, okay, we'll see that it actually ended up at 6.7 weight percentage of carbon, all right. So actually, okay, at this amount of carbon, okay, exists what we call as the intermetallic compound, right? So this intermetallic compound, okay, is known as cementite, all right. And the iron carbon system, okay, may be divided into two parts, okay, an iron rich portion, okay, as in the diagram that we have here, and the other, okay, which is not shown here, is for the composition between 6.7 and 100% weight percentage of carbon, okay, which is pure graphite, all right. So the reason why we stop at 6.7 is that it is appropriately labeled, okay, this way because, okay, beyond this, okay, it has no technological importance to the steel industry, okay. Why? Because in practice, okay, all steels and cast iron have carbon content of less than 6.7 weight percentage of carbon, okay. So that's why we only consider the iron and iron carbide system, okay, up to 6.7 weight percentage of carbon, all right. And in this particular phase diagram, okay, there are two very important invariant points. Okay, so the first one is at this point. Okay, so this is the eutectic point. Okay, because if we go along this vertical line, okay, from the liquid phase, okay, upon cooling, all right, so as the temperature drops, okay, so the changes, okay, will take place, okay, starting from liquid, okay, once it's actually crossed this line of temperature, okay, it will change, okay, directly into all solid, okay, without having to go into the transition phase, okay, on both sides, okay, of the point. All right, so if we write back the reaction, okay, it's going to be L liquid upon cooling or upon heating, okay, it's going to be resulted in gamma, okay, which is the austenite, plus Fe3C, which is the cementite. All right, so this is a eutectic reaction because it starts with all liquid, and then when it cross, okay, the temperature, it goes straight away to all solid. Okay, so this is a eutectic reaction. Okay, for iron and iron carbide phase diagram, the eutectic reaction occurs at 1147 degree centigrade. Okay, and the composition is 4.3 weight percent carbon. Right, so that's the first invariant point. Okay, and the second one, okay, is here, this point. Right, so if we look at the line here, okay, if we go along the line, okay, upon cooling, okay, that means, okay, from, let's say, from this region, all right, of austenite, okay, so once it passed this particular line of temperature, okay, so austenite will change into alpha ferrite plus cementite. All right, so if we write down the reaction, okay, so it's austenite upon cooling or upon heating, okay, it will transform into alpha ferrite plus cementite. Right, so let me just erase this a little bit so it won't confuse you. Okay, so it will change into alpha ferrite plus cementite. All right, and we know, okay, this kind of reaction, okay, is actually meant for eutectoid reaction. Okay, right, so this is the most important invariant point, okay, in steel industry as far as steel is concerned. All right, and it occurs at the temperature of 727 degree centigrade. Okay, and the composition is 0.76. Okay, 0.76 weight percentage of carbon. Okay, all right, so now, okay, let's move on. So if we look at the phase diagram, okay, of the iron and iron carbide here, let me just do some adjustment to this. All right, okay, so it can be if you are referring to the eutectoid point, okay, which is here. Okay, why we are referring to the eutectoid point? Okay, because this is where all the transformation, all the heat treatment that we are going to do on steel, okay, will take place. Okay, so to the left, okay, of the eutectoid point, okay, is called the hypoeutectoid steel. Okay, hypo means, okay, it occurs before the eutectoid point. All right, and to the right of the eutectoid point, all right, it's called the hypereutectoid steel. Right, because it occurs after the eutectoid point. Okay, so for all the composition, okay, of alloy, okay, for hypoeutectoid steel. Okay, let's have a look at the microstructural development, okay, that occurs, okay, upon cooling. All right, so let me just rub this off for you. Okay, so let's say, okay, let's work on this one because it's easier for you to see. Okay, so let's just choose one composition, all right, that we can within the hypoeutectoid range. Okay, so let's say we take this one line here. Okay, so this is the line of our alloy composition C0. All right, so let's say it contain around 0.25 weight percentage of carbon. All right, so basically it's a mild steel, okay, a low carbon steel. All right, okay, so in steel industry, okay, normally if we do heat treatment, okay, a process in which we can apply heat onto the steel, okay, in order to alter certain properties of the steel, okay, it always be in the starting from the austenite region. Okay, so we will heat up, okay, the steel, okay, into the austenite region. Okay, and the transformation that takes place upon cooling from the austenite region, okay, will actually determine the final properties of the steel. All right, so let's say, all right, we start here, all right, at temperature 1000 degrees centigrade. Okay, so this is the first temperature. Okay, let's work with the first temperature. Okay, our T1 is 1000 degrees centigrade. Okay, so this is the temperature line, this is the composition line. Okay, so at this point, all right, number one, okay, the phase present, okay, is austenite. All right, so we know it's austenite, so it's all austenite. So if we want to draw the what do you call it, the resultant microstructure, okay, so this is how it looks like. Okay, so we have like a few grains, okay, here made of austenite, so it's all austenite here. Okay, so it's in solid form. All right, so as the temperature decrease means the cooling, okay, is in progress. Okay, and it crossed this line. All right, so you can see this line, this is a surface phase boundary line. All right, so when it cross this line, it will go into another phase, okay, which is the alpha plus gamma phase. Means, okay, some of the austenite already transform into alpha ferrite. Okay, so how does the resultant microstructure looks like? Okay, so just now, all right, we know, okay, this is how the austenite looks like. All right, but then as we cross the phase boundaries, okay, some of the alpha ferrite will start to exist. Okay, so alpha ferrite, okay, within austenite, okay, will start to grow on the grain boundaries of the austenite. All right, it will start with small nodules. Okay, as the temperature decrease, okay, so it will start to grow bigger, okay, along the grain boundaries of the austenite. All right, so as the temperature going down, okay, before it reach this line, okay, so now, okay, the grain boundaries of austenite is actually now filled with alpha ferrite. Okay, and then once it crossed this line, okay, at 727 degrees centigrade, okay, which is the eutectoid temperature, okay, it will go into another phase, okay, which is called the alpha plus cementite phase. Okay, now the transformation that takes place, okay, in iron and iron carbide phase diagram, okay, as far as the steel industry is concerned, okay, always start from austenite. Okay, and it will be the austenite that is going to transform into something else, okay, upon cooling. All right, now just within the alpha plus gamma region here, okay, let me just make it a bit clear for you. Okay, within this region, okay, we have the alpha, okay, started to grow at the grain boundaries of the austenite. And then when we cross the eutectoid temperature at 727 degrees centigrade, and then we come to a new phase, okay, which also has alpha ferrite, but this time this alpha ferrite is combined with cementite. All right, so the resultant microstructure, okay, will look something like this. Okay, now, okay, this is the boundary, okay, and along the grain boundary of the austenite is already filled with the alpha ferrite that occurs before you reach the eutectoid temperature, okay. And then once you cross the line, okay, of the eutectoid temperature, everything, all the austenite will transform into alpha ferrite plus cementite. Okay, so alpha ferrite plus cementite is actually an alternate layer called lamella structure. Okay, so this is how it looks like. Okay, it's an alternate layer of alpha ferrite and cementite. Okay, so if we want to give some colors to it, so the yellow, the red one, okay, is the one representing the alpha ferrite. Right, and the black one is representing the cementite. Okay, so at this point, okay, we have here, okay, the alpha ferrite and cementite, okay, that actually comes after it crossed the eutectoid temperature. And then we have the the alpha ferrite on the grain boundaries, okay, that actually occurs before you cross the eutectoid temperature. So we have two alpha ferrite, right? So in order to avoid confusion between the two, okay, so the one that occurs before you cross the eutectoid temperature is called the pro-eutectoid alpha ferrite. That means, okay, it's the alpha ferrite that actually exists, okay, before you cross the eutectoid temperature. All right, and the alpha ferrite, okay, that exists after you have crossed the eutectoid temperature, okay, is given in the lamella structure of alpha ferrite plus cementite. Okay, and the whole thing here, alpha ferrite plus cementite, okay, has a special name. All right, and it's called perlite. All right, so that's how it looks like. Okay, the microstructure development, okay, for a hypoeutectoid alloy. Hypoeutectoid. Okay, that means all the composition that occurs before you cross the line for the eutectoid composition. Any composition, all right, as long as it cross the austenite, alpha plus austenite, and alpha plus cementite region. So it has the same microstructural development. All right, now let's have a look, okay, an example, okay, for a hypoeutectoid composition. Okay, so let me just rub this off so you won't get confused. Let me quickly do this. Okay, now for hypereutectoid, it means that the composition actually comes after, okay, the eutectoid composition. Means the composition is actually more, okay, than the more in the percentage of carbon compared to the eutectoid composition. Okay, so it can be from here, okay, to here, somewhere here. All right, so this is the range for hypereutectoid alloy. Okay, so let's just say that we choose one composition. Okay, so let's say we choose here. Okay, because this is the eutectoid point. Okay, so it's hyper because it occurs after the eutectoid composition. All right, so let's say this is at 1.5 weight percentage of carbon. Okay, so now, okay, let's start from the austenite region, because we always start at the austenite region for steel, okay, for the heat treatment of steel. Okay, so upon cooling, okay, at first, okay, it's in the all austenite region. Okay, so when it's all in the all austenite region, okay, so the microstructure, okay, will look something like this. Okay, so this is the grain for austenite. All right, so it's 100% austenite. Okay, and as the temperature decrease, okay, it will cross the phase boundary. All right, so once it crosses the phase boundary, it goes into another phase, and this phase is called the austenite plus cementite. That means some of the austenite, okay, already transformed into cementite. So let's look how, okay, it actually looks like, the microstructure. Okay, so still we have here the austenite, and then you add up the cementite. Okay, so cementite, okay, actually exists, okay, on the grain boundaries of the austenite, the same thing as in the previous case. Okay, but in this case, okay, it's no longer alpha ferrite, but it's now cementite. All right, so the amount of cementite that occurs, okay, on the grain boundaries of the austenite will grow as the temperature decrease. Okay, so once the temperature, okay, is crossing this line, okay, which is the eutectoid temperature, so when it's actually go below the eutectoid temperature, it will come into another phase, and this phase is the one that contain the alpha ferrite plus cementite. All right, so that means, okay, just before it crossed the line, okay, all the lumps or nodules of cementite here, okay, will already filling in the grain boundaries of the austenite. All right, so it looks something like this. Okay, so it looks exactly the same. It's just that this time, instead of this is alpha ferrite, now it's cementite, and the remaining is still austenite, right? But once it crosses the eutectoid temperature, okay, so it will the remaining austenite will change into alpha ferrite. So this is how it's going to looks like. Okay, we already have the cementite, okay, which occurs before you cross the eutectoid temperature, okay, the one that occurs along the grain boundaries. Okay, so this is cementite, and then once it crosses the eutectoid temperature, okay, all the austenite will change into alpha ferrite plus cementite, and we know alpha ferrite plus cementite is actually the lamella structure of alternating layers between alpha ferrite and cementite. So let's just quickly do some colors here to actually differentiate between the two. All right, so now we can see that the black color one is the cementite, okay, and no, yes, sorry, the black color one is the alpha ferrite, okay, and then maybe we can put on the red colored, okay, to represent the cementite. So in this case, for hypereutectoid alloy, we have two cementite. Okay, one is, okay, the one that is actually occurs, okay, on the grain boundaries of austenite before you reach the eutectoid temperature, and the other one, okay, is the cementite, okay, which exists as a lamella structure or the alternating layers, okay, between alpha ferrite and cementite. All right, and the whole thing, okay, is actually known as perlite. Okay, so the alpha ferrite, the alternating layer or the lamella structure, is also known as perlite. All right, so this is also known as perlite. Okay, so that's how the microstructural development will looks like. Okay. All right, so I think okay, then before we go, okay, let's just try to look at one example, okay, that actually um, concerns, okay, the phase analysis, okay, for the iron and iron carbide phase diagram. All right, so let me just rub off everything, because all of this is actually available here, okay, in your notes, okay. It's the same thing, it's just that I just try it, scribble it on a fresh uh, phase diagram, okay, to make it clear for you. Okay, now let's try and do a phase analysis, okay, um, for a hypoeutectoid steel, okay. So let me try to, okay, increase this one, right? Okay, all right, so let's say we want to choose a composition of hypoeutectoid alloy of maybe 0. Let's say it's 0. Maybe 0.3%, shall we? Let's say this is 0.5 and then this is 0.3. Okay, let's say, okay, for argument's sake, let's say this is 0.3. Okay, it's not accurate, but yeah. Okay, so let's say this is 0. Let me choose. Okay, it's, sorry. Okay, so let's say this is 0.3 weight percentage of carbon. All right, so this is our C naught. Okay, so let's do a phase analysis. Phase analysis means, okay, you're going to need, okay, all the 4 important information that we have looked so far, all right, in the previous lecture. Okay, the first one is the phase present. The second one is the composition of each phase. Okay, third one is the weight fraction of each phase, and the fourth one is the resultant microstructure. All right, so let's say, okay, we are going to look at these 4 things, okay, at various temperature. Oh, sorry. Hold on, what happened? Okay, so sorry about that. Okay, let's say we're going to look at it at various temperature. Okay, so let's say the first, so the item 1, 2, 3, 4, right? So let's say the first temperature is let's say 850 degrees centigrade. So let's say it's 850 degrees centigrade. All right, so first thing that you have to do is to draw the temperature line that will actually intercepts with your composition line. All right, so you look at the this point, okay, the intersection point. All right, and now you look at the phase. Okay, so now here this point is within the austenite phase, so it's all austenite. All right, so the phase present is all austenite, or we can say 100% austenite. All right, number 2 is the composition of each phase. Okay, so it's 100% austenite. All right, and the weight fraction of austenite is 1. okay, because everything is austenite, and the resultant microstructure is, okay, you have the grain of austenite, okay. And then let's say, okay, we take another temperature, okay. The second temperature is let's put it as maybe 820 here. No, sorry, it's 780 here, 700 and maybe 760, sorry, okay. So let's say this is 750. All right, so this is 750 degrees centigrade, right? So now the intersection point, okay, between these two is here. All right, so that point, okay, is within the alpha plus austenite region, okay. So the phase present, what have I done? Okay, the phase present is alpha plus austenite. All right, I've done something to this, don't know what. Okay, let's just put it back where it should be. All right, okay, now okay, so let's say it's austenite plus alpha ferrite, right? Now when it is in the two phase region, okay, we can apply the lever rules, okay. So let's just quickly do the lever rules here. All right, so lever rule needs 3 points, okay, to become a lever rule. So use 1, 2 and 3, okay, because this is the line, okay, that cross these boundaries, okay, and this is the point that cross this boundary. All right, so we have the C naught here, okay, and here we know the phase present is austenite plus alpha ferrite, so one must be C alpha and the other one must be C gamma. All right, and we look at this point, okay, beside it is the area for alpha ferrite, so this is for C alpha, and this area beside it is austenite, so this is C gamma. All right, and the composition, okay, is this here and here. Right, so since this point, okay, is very close to the solubility limit of carbon in alpha ferrite there, okay, so we can take it as 0.022, okay, and our C naught is 1.5, okay, and our C alpha is around maybe 0.7. I think it's already no, sorry, this is not 0, sorry, this is 0.3, okay, this is 0.3, okay, and maybe this point is 0.6. Okay, so next, okay, we have to get the weight fraction, so we have to get the weight fraction for alpha, and we also have to get the weight fraction for gamma. All right, so if we draw back the tie line there, okay, so this is for C alpha, this is for C naught, and this is for C gamma. All right, so this is 0.022, and this is 0.3, and this is 0.6. okay, so in order to calculate the weight fraction, okay, you can always go back to the notes, okay, to look at the way it's being derived, okay, the formula, or you can always do the shortcuts, okay, and play with some tricks, okay. So W alpha, all right, so we are going to find the weight fraction of C alpha here, okay, is equals to the length of the opposite for, okay, of whatever we are going to figure out, okay, in the tie line. All right, so it means, okay, if we are looking for C alpha, we need to get the line of the opposite of it, okay, which is this length. Okay, so this length is actually C austenite minus C naught, right, over the total length of the tie line. All right, the total length of the tie line is C gamma minus C alpha. All right, so C gamma is 0.6, C naught is 0.3 minus 0.6 over 0.6 minus 0.022, and there you go. You'll get the answer for W alpha. All right, and the same thing goes for when you want to calculate the weight fraction of gamma or the austenite. So it's equals to the, okay, again, if this is the sorry, I keep on doing this, don't know why. Okay, if this is the point for C gamma, okay, so in order to calculate the weight fraction, we need to get the opposite length, okay, on the tie line. Alright, so this length is C naught minus C alpha, okay, over the whole length again of the tie line, okay, which is C gamma minus C alpha. Alright, so it's actually 0.3 minus 0.022 over 0.6 minus 0.022. Okay, alright, so there you go, you'll get the answer. Okay, so if you want to check, okay, W gamma plus W alpha should be equals to 1. Alright, so if you get it 1, then most probably you are on the right track. Okay, so you can do the same thing, okay, for other temperature as well. Alright, now let's say, okay, if we have let's go to maybe the question here. Alright, so the example problem here says, okay, for a 99.6 weight% of iron and 0.4 weight% of carbon steel at a temperature just below the eutectoid, right? So you have to determine the following, all right? The fractions of cementite, okay, and the fraction of the total ferrite. Okay, so this is the total ferrite. Okay, and the amount of cementite, okay, in grams, okay, that forms in 100 gram of steel, and the last one is the amount of perlite, okay, and proeutectoid ferrite. Okay, so let's have a look. So let me just crop this off, okay, so it's easier for you to see. Alright, now you are asked, okay, about the fractions, okay, the weight fractions, okay, of the resulting microstructure at temperature just below the eutectoid. Alright, so this is the line, this is the alloy line, the alloy composition line here. Okay, so this is the alloy composition line. Okay, so the problem says that it's at 0.4, okay, weight% of carbon. Okay, so that's your C naught. Alright, and this is the eutectoid temperature. Okay, so we are going to calculate it just below the eutectoid temperature. Okay, so if this is the eutectoid temperature, okay, it's just below. Alright, so it's like 727, okay, minus delta T. Okay, just a bit difference, okay, a bit lower than the eutectoid temperature. Eutectoid temperature is at 272 degree centigrade. Alright, so using the tie line, okay, just below the eutectoid, alright, so you'll get the C alpha. Alright, so you'll get the tie line here, okay, So this is your C naught, okay, and this one, okay, will be your C alpha, because next to it is the alpha region, and here is the C for the composition for cementite, because it's actually reaching the line of the intermetallic compound at 6.7. All right, so C alpha, okay, is very close to the solubility limit. Okay, so we just take the value of 0.022 weight percent carbon. Okay, we have 0.4 here, and the C cementite, okay, is at 6.7 weight percentage of carbon. All right, so using the level rule, okay, we can calculate the weight fraction of the cementite. Right, so again, okay, if you want to follow this, okay, you can always follow it, but if you not, if you like want to do some shortcuts, okay, so you just look at your tie line here, and then you know you are looking for the weight fraction of cementite. Okay, so you need to get the line okay, on the opposite side of the tie line. Okay, so it's C naught minus C alpha over the whole length of the tie line, okay, which is C cementite minus C alpha. All right, so you'll do the calculation and you'll get into this. Okay, so this is the amount, the weight fraction of cementite, okay, just below the eutectoid temperature, okay, at the composition of 0.4 weight percent of carbon. All right, so since we have 100 gram of steel, okay, so we just times everything with 100, and then you'll get 5.7 gram, okay, of cementite. All right, okay, now for the third one, okay, the amounts of perlite and proeutectoid ferrite. Okay, so perlite, we know it actually consists of alpha ferrite plus cementite, and then the proeutectoid ferrite, okay, is the ferrite, okay, that actually occurs along the grain boundaries of the austenite, okay, before it actually reach the eutectoid temperature. Okay, so this is alpha proeutectoid alpha ferrite. Okay, so let's have a look. Okay, so using the VX tie line, okay, so let me just clear this out for you. All right, now why are we using the shorter tie line now? Okay, in order to calculate the amount of alpha ferrite, okay, and the perlite. All right, so the reason being is that, okay, if I can just increase the thing, okay, so just now, right, we are looking for the amount of cementite. Okay, so that's why just below the temperature of eutectoid, okay, it stretched, okay, from here, okay, no, sorry, it stretched from this point up to this point. All right, because we are looking for the whole thing, it involves cementite, right? But then, okay, in this case, okay, we are only asking for the fraction of ferrite, okay, the proeutectoid ferrite, okay, and the perlite. Okay, so the the proeutectoid alpha ferrite, okay, only occurs, okay, to the left hand side of the eutectoid point. All right, so here, okay, on the hypereutectoid steel range, okay, there's no more proeutectoid alpha ferrite, okay, because proeutectoid alpha ferrite actually occurs only within, let me see, only within this area, this small area. Okay, so the limit is at this point, okay, at the composition of the eutectoid composition. All right, so that's why, okay, the tie line now only stretch from here to the eutectoid composition, so it stretch like this. Okay, still your C naught is 0.4 weight percent of carbon. Okay, and this point is actually very close to the solubility limit of 0.022, okay, weight percent of carbon. So this is C alpha, right? And then let's have a look. Okay, and this is C gamma. Okay, so within, okay, just before it actually transform, okay, so this is the amount of proeutectoid alpha ferrite, okay, that we have. All right, so using the Leber rules, okay, so 0.4 is the C naught, okay, C alpha is 0.022, okay, and then we have C gamma, okay, which is at 0.76. This is, sorry, I was 0. Hold on, let me just write this. All right, so here, okay, so the C gamma is 0.76, okay, minus the C alpha. All right, so we'll get to the 0.512, okay, and the amount of perlite, okay, okay, this is for the perlite. Okay, so the amount of perlite is 100 gram, okay, times, okay, whatever it is that you get from the calculation of the weight fraction of perlite. Okay, I'm sorry, it's not of ferrite, it's perlite. Okay, all right, so that's the amount of perlite, okay, that you get, okay, by 100 gram of steel. Okay, so let's just go back. All right, so I think that's it, okay, for iron and iron carbide phase diagram. All right, and as a summary, okay, phase diagram, okay, are useful tools, okay, to determine the number and types of phase present, okay, the composition of each phase, and the weight fraction of each phase. Okay, so given the temperature and the composition of the system. Okay, so the microstructure of an alloy depends on its composition and whether or not cooling rate allows for maintenance of equilibrium. Okay, so there are important phase diagram transformation, okay, that include eutectic, eutectoid, and peritectic. All right, so I think that's it for to conclude chapter 7. Okay, I hope, okay, you'll be able to go back, okay, to your notes, okay, and find out, okay, more of the details, okay, for the chapter, okay, in order to better understand the chapter. All right, so I think that's it. Okay, thank you.